Hello, welcome to my lab report. Today we investigate 2D motion by comparing real-world data with two computational models, one with gravity alone and another adding air resistance. Using video analysis, computational modeling, and then applying core physics concepts such as the momentum principle, projectile motion, and natural forces such as gravity and drag, we'll discover that air resistance significantly alters projectile motion, reducing range and creating asymmetric trajectories, which the gravity-only model fails to predict. Let's recall the core physics at work here, the Newton's second law. As shown here, force equals mass times acceleration governs all motions in this lab. In the gravity-only model, the only force acting is the downward pull of gravity. But in the real world, objects such as our paper roll also experience air resistance. This drag, which is shown in this here in the formula, this drag force always opposes the direction of motion and grows stronger as the object moves faster. So what's the key consequence? Terminal velocity. The speed where drag force exactly balances gravity, causing the object to stop accelerating downwards. This fundamental difference between the two models is why we see such dramatic changes in the trajectory when air resistance is included. To ensure accurate modeling, we standardize our experimental condition. The projectile, which is our small paper roll, weighs 0.085 kilograms, was launched in front of this 13-inch MacBook Air, which serves as our reference scale. The lab class dimension, which is 0.304 meters wide by 0.215 meters long, allows us to calibrate tracker spatial measurements. We analyze the motion in the second quadrant of our coordinate system, tracking position data at precise fraction of a second intervals, which is around 30 frames per second. Here we have two graphs showcasing both how X and Y components are changing over time, and here is the video of the paper roll in motion. Okay, going over my GlowScript code, I do want to make it clear that I set my computational model to have gravity and drag, and this set the drag proportional constant to 0. Then left with gravity as the only force on my object as one of the model, essentially combining both models in a single code. We implement two simulations, one with gravity alone, where the drag is default to 0, and then adding air resistance, where the drag coefficient is now 0.008. The key differences lies in this conditional block, where drag is enabled. We calculate a velocity-dependent force opposing motion using the drag force, which is the negative b times speed squared in the direction of the velocity unit vector. Otherwise, the drag was just default to 0. Okay, to get a better visual of the code here, because we have the drag coefficient is set to 0, and we have our key difference here with the drag coefficient is set to 0.008 for the realistic model. This number determines how strong air resistance effect is. Here, we always calculate gravity pulling down, and if drag is enabled, we add an extra force that pushes opposite to the ball's motion, growing stronger as the ball moves faster. Here, for every fraction of a second, we update the ball's motion. The total force divided by the mass gives us acceleration, which changes the velocity, which then updates the position. This is achieved by using both the position and velocity update formula, which is shown here. I also added my own experimental data into my model for the sake of comparison after I run the code. Okay, let's run it. So here's the object roll in motion, and here is all three of my models side by side, and then I have the data that's being generated by the program. Here is the drag data, and here's my gravity only data and my drag plus gravity data shown here. Here is all the data side by side between the three models. As you can see, there are significant differences, which we will discuss on our next slide. So between the models, we notice a significant difference between the maximum height and the range, which is calculated by the paper's displacement. Furthermore, while the gravity-only model, which is shown in this bluish color, predicts a symmetric parabolic arc with an overestimate range of negative 1.27 meters. The experimental data, which shown in red, shows a shorter negative 1.06 meters range but a higher 0.7 range peak. Likely due to unmodeled lift effects, the gravity plus drag model, which shown in green, closest matches reality at around negative 1.04 meters range, demonstrating how air resistance both shortens distance by about 18% and then creates trajectory asymmetric through energy loss. Okay, let's dive into our lab questions. So to answer our what does it mean regarding terminal velocity question, so first, the terminal velocity occurs when air resistance balances gravity, where F net equals 0. The gravity plus drag model predicts this perfectly. The velocity stabilized at terminal velocity, which is calculated here, at 2.48 meters per second, calculated from square root mg divided by b. In contrast, the gravity-only model fails to predict the terminal velocity shown here. It just keeps going indefinitely, which is highly unrealistic since it has an indefinite acceleration. Let's see, the model here matches the real-world behavior where light objects such as our paper roll matches at maximum speed, while heavy objects and vacuum keeps accelerating. Therefore, drag plus gravity models predict a terminal velocity, but not the gravity-only model. Now answering our what if question, when object is thrown straight up, like here, with the same initial speed as in the angle experiment, its total time, which is calculated through our famous kinematic equation, in the air is shorter, just 0.22 seconds compared to 0.43 seconds for the projectile motion. This is because in the vertical motion, there is no horizontal velocity component to sustain drag. Allowing gravity to dominate the descent without drag, the theoretical time 0.254 seconds matches the expected the 2 times initial velocity over gravity, but the drag reduces it by further 13% by making the descent faster than the ascent. In contrast, the angle throw experiences prolonged airtime due to drag acting on both horizontal and vertical motion, slowing it down overall, thus purely vertical throw reaches the ground faster. Here are the potential errors that might have occurred during the experiment. Initial velocity uncertainty from the variation in the throw, lift effect due to the paper's shape altering airflow, camera's parallax error from the slide angle misalignment, and the simple drag modeling, which ignores turbulence. Together, these errors can influence our data, thus presenting inaccurate results. In conclusion, this experiment highlights how Newton's law combined with the quadratic model, drag model, where F net equals ma minus b v squared explains the observed motion, including the objects reaching terminal velocity at 2.48 meters per second. Matching theory. The drag's impact is pretty clear. It reduces range by 18% compared to the drag-only model and creates an asymmetric trajectory with a steeper fall. These insights matter because real-life projectiles, especially light objects like a paper or a drone, are heavily influenced by drag, requiring accurate modeling for projections. However, our simplified drag coefficient, where b is set to 0.008, ignores lift and spin effects. So this will ultimately leave room for refinement, and drag transformation idealize the physics into the real-world behavior.